Okay, so in this short video, we're going to summarize what we learned from the PowerPoint presentations on the applications of the various parts of the electromagnetic spectrum. So this is just a way of summarizing what we talked about, so you have something on paper. So let's start with radio and TV. The most important application, it can be summed up as telecommunications. I'm just going to write as telecom. Okay, cell phones, Wi-Fi, Bluetooth, traditional radio, television falls in there. Okay, so it is revolutionized, especially your lives, my life, for the past generation, and it will continue to do so. The ability to send energy and information across great distances, because radio waves have a lot of advantages. They can travel through the atmosphere very easily, not blocked by clouds. They're not easily blocked by buildings or other objects of diffraction. They can penetrate most materials because of resonance issues. In other words, the frequencies at which many materials vibrate does not overlap radio waves at all. Okay, so there's much to be said about them, but they can be summed up as telecommunications. We also mentioned in class this most likely way we think, we have no idea, but which extraterrestrials would communicate with us, because radio waves have huge advantages, even astronomy, for telecommunications. We mentioned in class, even our broadcasts of television are still beaming out to space 10 years, 20 years, 70 years since we really started first broadcasting. Microwaves are more than just the oven, okay? They are very important in telecommunications as well, just like radio. All right. Again, for shorter waves, they have slightly different applications, but they all kind of fit in with radio. Other applications you may not realize is radar. Okay, radar is an acronym where they call it radio, but it's really in the microwave part of the spectrum that can send short waves, bounce off an object, come back, and you can locate where they are. And that short wavelength is important for that. And of course, for microwave ovens, what are you really heating up? You are heating up water molecules. Okay, not ice, not really anything else. And when those water molecules, because they're overlap in frequency with microwaves, they will absorb, resonate, big amplitude, which is thermal energy. Next, infrared radiation. So we've skipped, if you know, oh no, I haven't got there yet. So infrared are the basis for, and this will be very important later on in the year, for the greenhouse effect. Okay, so the greenhouse effect, in very simple terms, is we get visible light gets into the atmosphere, it's absorbed by the Earth, and then because the Earth warms up and its temperature, I alluded to this earlier in the previous one, it will give off radiation, and the radiation the Earth emits is infrared. In certain gases in the atmosphere, greenhouse gases will be trapped some of that infrared, and that will cause a warming effect. By and large, that warming effect has been very good for the humans and all other critters. It's just recent increases, very rapid increases in the past century have made things potentially dangerous. Another thing we can look at is the thermography we saw, the ability to see warm objects in the dark, because we're all glowing in infrared. In fact, infrared is what you feel as heat very often from a source. Ultraviolet, primary cause of sunburn and skin cancer. Okay, and this used to be an old person's disease, but we're seeing dramatic rises in young folks. That's you guys, or 20-somethings, because of the prevalence of tanning beds. And we're starting to see more regulation with that industry, but it's still a big deal in many parts of the country. Ultraviolet also has nice use with sterilization of medical instruments. It's a good way of killing germs, because most life cannot withstand ultraviolet radiation, because it is actually all three, these last three, and this is important to know, are ionizing radiation. And I'm going to talk more about that in a second with X-rays. Okay, so X-rays and gamma are generally dangerous to life forms because they ionize. They have enough energy that they'll ionize your cells in particular tissue that hits it. When you ionize the chemicals within the cells, you disrupt the chemistry that will generally kill the cell. When you kill enough cells, then you start getting sick. Worse yet is you can create mutations in DNA. And those mutations generally are not good. Okay, they can be deadly or they can be completely innocuous, but they rarely help you out. So exposure to especially these three types can lead to those. But their positive use is taking pictures of hard and soft tissue. Okay, so many of us have had X-rays. of bones if we've broken something or think we have, and definitely of our teeth. The hard tissue will cast shadows. X-rays will pass through soft tissue, and we can, from that, learn how to study it. Another thing you might not realize, but it's actually very, very important in many applications, is crystallography, understanding how crystals are shaped by using the structure of minerals and such, by shining X-rays through them and looking for diffraction patterns. Very, very powerful technique. Lastly, gamma. Okay, so gamma, when we hear the word radiation, people think nuclear, dangerous, etc. What they're really associating with is gamma radiation, which is generally very, very harmful. It's the most dangerous of them. It's the highest frequency, shortest wavelength. That doesn't necessarily explain why it's the most dangerous. We'll talk about that with more of the modern physics. But it is associated with nuclear energy and weapons. You do not want to be exposed to gamma radiation. It is highly ionizing, therefore highly dangerous. Acute exposure to it can kill you, or it can cause radiation sickness, like the unfortunate people from Japan who were exposed to dropping the 2 atomic bombs. Or over the long term, it can cause mutations, cancer, etc. There are some medical uses for gamma radiation. One that I don't have here, that's part of the radiation therapy for cancer patients. You target the cancer cells with that radiation, hopefully kill them and not your healthy cells. And another interesting use is medical imaging. Okay, it's an alternative to X-rays or MRIs and whatnot. And what you basically do is you drink a radioactive dye, let it flow through your bloodstream, and then you're glowing, very weak output of this, but you can look at a gamma scope to see where the radiation is, and if it concentrates in certain places, you can maybe see some issues that you couldn't pick up with X-rays. Okay, so that's just a simple summary of the electromagnetic spectrum and how they're applied here on Earth. I didn't talk about the astronomical stuff. We did that in class. Hopefully that gives you a pretty good idea.